Hello guys, as you know that my name is Shadi Hasan and I started a series of explaining Aveva Pro 2 process engineering on my channel Smart Process Engineering. In my last video I explained that how one can perform face envelope utility and understand that how the heaviers in the gas stream um, may condense in the line when its temperature is reduced to below its dew point. So in this video I have a plan to explain that how a De-Ethanizer column can be designed, and for completing this task there are certain assumptions like that the C2 means that the ethane removal from the top should be 99%, and the propane will be removed from the bottom reboiler stream as it is shown here in the flow diagram. That this how the simulation will look like after converging into the Pro 2 Aveva software. So what we are gonna do is the bottom purity is defined by an ethane to propane ratio of 0.025. So there are certain feed properties which we have to add in the feed stream uh, to make it converge. So there are certain or some theory available with respect to this simulation, that there is a design trade-off between the capital and operating costs. Capital cost depends on the number of stages, obviously, which determines the height and on the diameter of the column. And operating costs depend on the condenser and boiler loadings. In order to develop a relationship between capital and operating costs, a number of runs with different column height stages is required. So in this simulation, uh, the theoretical number of stages are considered as 20, including the condenser and the reboiler. Uh, so we will perform this simulation in the latest version of Viva Pro 2 2020, and we have some process data available which we will be used in the simulation. So this is the gas stream composition is available. So let's start with the developing or the building up the simulation model in Aveva Pro 2 process engineering, and then after completing the model we will then discuss that how to optimize the column diameter with respect to the height. Okay, so the gas stream composition is given here. There's some process conditions like feed uh, pressure is 440 psig and it's 30% mole vaporized, means that 70% is the liquid fraction. Is at the condenser is at the dew point and bottom is at the bubble point. Okay, so SRK has been chosen to calculate equilibrium enthalpy and vapor density, and we have to modify the thermodynamic package with respect to the liquid density, and we will choose Lee Kessler. Okay, the simulation model, 20 theoretical stages as I explained earlier. A thermosiphon boiler is required. Okay, so we will use the pump round heater in the bottom tray with a return stream vapor fraction of 0.35, means that the stream which is coming from the reboiler must have this vapor fraction. So the feed is flashed at the feed tray pressure, vaporizing under tray 9 and liquid dropping on tray 10. So the feed stream drops on this tray 10, or so the total trays is 20. Okay, so this is how the Component selection dialog box is available in the Pro 2, and we have to select our desired components from the list available. Then we will, in the second step, we will usually select the thermodynamic package, uh, and then we will start building the model by selecting the stream first. We will put this total flow rate, then the composition available in the first slide. Then we will modify this column data one by one, and let's start from the step 1, building the stream by entering the composition. Okay, so here's the composition. Okay, so new, component selection, select from the list, Okay, so we have developed the feed stream and connected that stream with the column with 20 trays, and we all have also added the stream 2, which is De-Ethanizer bottom and the top De-Ethanizer. Okay, so now we are going to entering the data into um the main column. Number one is the pressure profile. So the top tray pressure is given here, which is 425 in PSIG gauge. So we will convert this unit into PSIG, and column pressure drop we select 10 psi. It's also given in the file. Okay, feed and products. So feed is entering in at tray 10. uh, so we have already done these steps, and so the overhead rate is set at S2 is the overhead here, and S3 is, so we can do this also. So we will delete this stream again and add stream, top stream first, and this stream second. Okay, now again we will go here at stream 10. Now it's matching to overhead. Estimate rate is 540, so we'll select this. I'll write this here and then okay. No, and then okay, performance specification. As I discussed earlier in the starting of this video, that at the bottom spec we will set 0.025 fraction of C2 by C3, means that ethane to propane ratio must be set at 0.025, and the second specification is related to the propane uh, in the stream 2, means in the overhead. So the specification here is that the propane in the overhead should be limited to 1% with respect to the feed. So it means that whatever the mole percent of C3 in the feed, it should not exceed by 1% in the overhead. So we will set this two specification here one by one. Okay, now as a part of this uh, tutorial, we have to attach a pump around to the reboiler. So there is a option available for the pump around. Add pump around 1 tray 20 tray 20 0.65 heater name 2. Okay, and change the units of pressure. Okay, so the specification we have entered that the exit stream of the reboiler should have 35% of vapor which is returning to the column. Okay, so we don't need any other reboiler in this column, so we have removed this column with reboiler. Okay, so this column parameter we will change this to pump around. Okay, active. Okay, so in the next phase we will put some data in the tray hydraulics packing for the sizing. We will select the sieve trays and find out the diameter of the column above the feed tray and below the feed tray. With 82% flooding in the trays is assumed, so with 18-inch sieve tray spacing. So it depends on your cases and the way you are looking at the column and specifications or the requirements from the end user will help you to fix this uh, flooding setting and the column diameters. It also depends on the design and if there is a debottlenecking, then uh, this modifications and reassurance with this tray hydraulics packing is essential to perform good hydraulics and to understand the pressure and condenser profiles. Okay, so starting tray 2 we will set this 9 and 9, starting tray 10 and 19. Sizing, we are selecting the sizing option. Okay, enter data, sieve trays, it's 18-inch, minimum tray diameter and 18 tray spacing. Perform tray sizing condition output time, padding is 82%. Okay, enter data, same data we will add here also. 18 minimum tray, 82 threading and output time. Okay, so we have entered all the data into the stream. Now we will put some description here. De-Ethanizer, Okay, and so it is converged because this blue color shows that the column is converged now. So we have done this. Now for analyzing that diameters of this column, we have to see the output reports. Generate tax report. So here is a detailed report of the column with the tray sizings and diameters and other requirements and input data which we put at the beginning of the simulation, like the composition and temperature pressures. Okay, so here is the diameter. Let's read what report says and what are the results. The capital cost of the column depends on its height and diameter. Okay, the height is a function of the number of trays. The diameter of 20 theoretical stages are 30 inch above the feet and 54 inches below it. Okay, so at theoretical stage 10, the feed is entering, and above that the diameter required is 30 inches, and below that the diameter required 54 inches. And I think this 54 inches is below this stream 54, and this 30 inch is on the top. So it means that our simulation is correct and it's giving the same results as in the tutorial. So the conclusion is that the simulation shows the result of diameter and duties for one specific column height. Okay, so the column height is one specific. The column cost is obtained from height and diameter. The column duties determine the capital cost of the condenser and Reboiler as well as representing the major operating cost. You will need to run cases at other column heights to determine the capital operating cost relationship. So it's just an example of understanding that how one can do things like how to calculate the diameter of the columns through tray sizing utility in the Aveva Pro 2 process engineering. So it gave us a direction that how we can calculate the capital operating cost of the columns through the relationship of height and diameter. So um, if you have if you want to run many other cases as per your requirement, then you can also do that through the same procedure, and for the output you can generate report as I already did this. So we usually get this kind of report here, and the reports is a kind of notepad, um, so it can be printed and you can also save it in PDF. um, so this is our today's tutorial. Hope you like it, and thank you for watching this video, and stay tuned for the next tutorial of Aveva Pro 2 process engineering. Hope you understand this very well. If you have any questions, so you can write it down in the comment section, and thank you very much.